Hi, everybody. Today's lecture is not actually a lecture, it's just a review session. So, if you have any questions that you would like me to go over about anything from chapters 6 through 10, please type it in the chat. I'm gonna let the music just keep running and give us time to accumulate some more questions, since there are none right now. And I'll go through all the questions in the order that I get them. So, hope to hear from you in just a bit. And go ahead and just type whatever in the chat so I know what to work on. See you in a little bit. Alright. This looks like enough to work with for now. I see a few duplicates in here. So we'll get to those as we get to them, I guess. I'll just be like, oh, we already did this one. Okay, so, oops, nothing on that screen. There's no lecture, so what I'm going to do is, where is my, there it is. Can I just do this? Oh, that's the bottom of the screen, actually. I guess I can't really make this any bigger, so we'll just put it where it is. Okay. Set that back to where it was. Okay, cool. All right, so I'm going to just go down these questions one at a time. So let me scroll up a little bit just so that it doesn't kick me off here. So this is where we'll start. So balance the equation. So let's write the equation down real quick. And then we can do the question. So first we got to balance it. So I'm going to count up C's, H's, and O's on both sides. Okay. First thing I'm going to do is I'm going to try and balance carbon. So since this is the only place the carbon shows up, I'm going to try doing this and see what happens. So 5 CO2 would make 5 carbon. 5 times 2 plus 1 is 11 oxygen. And then I'll try and balance out H. Well, H only shows up right here, so I got to put a 6 here so that I get 12. And then I have 10 plus 6, or 16 oxygen. And to get this side to be 16, I go like this, 8. So my equation is not balanced. And then, oh, when I click off of that, the question becomes unreadable. So this is the one we're working on. And if 7.42 moles of C5H12 are reacted with abundant oxygen. Oops, let me try that again. How many moles of H2O are produced? So we know that if I want to figure out the number of moles of H2O, I can use the balanced chemical equation to do that, right? And I know that for every 1 mole of C5H12 I put in, I get 6 moles of water out. So whatever this is ends up being is the answer. So 7.42 times 6. Looks like the answer should be 44.5 moles of water. So that's the first one. And then there was a duplicate of that somewhere down below where somebody asked if you use 5.01 moles. You could just put 5.01 here. 5.01 times 6 would be about, it would be 30.6. Okay, so that's that one. When to use Boyle's law versus Charles' law versus combined gas law versus ideal gas law. So for gas laws, you virtually never need to use Boyle's or Charles' law when you have the combined gas law. So this is the combined gas law. And so you use the combined gas law for any problem that has a before-after situation. So it might say, like, initially the volume was 21. Then after compressing, the volume is now 7. What's the pressure? Or something like that. And so really all you have to do is just make a giant chart. PVT, 1, 2. and start filling in numbers until you are left with something that you have to solve for. Now, if you have a circumstance where you're doing a combined problem, or a before-after problem, I should say, and you realize, well, wait a second, it doesn't say anything about temperature, or it says the temperature is constant. If it's constant, then it doesn't apply to the problem. So you just draw a line through it. So maybe I ask you a problem about, like, okay, I expand the piston at constant pressure. What's the new temperature? And you might, okay, what do I put in for pressure? Well, if the pressure is constant, you don't have to put in any numbers at all. You just cross those variables out. Alternatively, what you could do is you could say, well, if the pressure is constant, and I put the same number in on both sides, because it's constant, right? Then when I divide them out, they just cancel, right? That's why I'm doing that sort of process here. So for any gas law problem that has a before-after situation, just use the combined gas law. Charles' law and Boyle's law are helpful for us making the gas laws, but on their own, they're just sort of, I want to say niche. It's like, oh, that's quaint. We have a law that works just for volume and temperature. The ideal gas law, on the other hand, you're going to use this for where that you don't have a before-after, or otherwise a one-time equation. So, like, at this moment, I have a balloon that has this volume and this pressure and this number of moles. What must the temperature be? So if you are doing a problem and you see that you have one of every variable and not two of most of the variables, you're going to use the ideal gas law. In the ideal gas law, n is the number of moles. So if I said a balloon contains 30 moles of helium, n would be 30. Now, if I said n equals 30 grams of helium, then you have to turn the grams into moles using the molar mass on the periodic table. Okay, so that's gas laws for now. If you have a specific gas law question that you'd like, go ahead and type it in the chat there. We'll go over that when we get down the list there. So we got acetaminophen for this next one. NO2. I bet that's an A. I'm misspelling it. Oh, there we go. Acetaminophen. There we go. All right. So I have 277.1 milligrams. That's important. Of acetaminophen. I'm just going to label it that AC. What mass of this is hydrogen? Oh, I'm going to scroll this up just real quick so that it doesn't move on me while I'm trying to read it. So keep typing. You see my little giant blue arrow down there. So I will get your message in just a second here. So for this problem, so I got milligrams of acetaminophen. Obviously, I need to turn that into grams of acetaminophen so I could do anything with it. Remember that whenever we have one of these A-B problems where we have a starting quantity and we want to figure out what we need to turn it into, the answer is always moles, right? So moles of acetaminophen. And then I can do, if I know the number of moles of acetaminophen, I know the number of moles of hydrogen because I have the formula here, right? And then finally, if I know the number of moles of hydrogen, I know the mass of hydrogen. So let's just turn this into grams real quick. In a milligram, there are 10 to the minus 3 grams. And so now we can do the problem. So I can turn grams into moles. And the way that I do that is I look up the molar mass. You probably remember about Lentech, where you can get the molar mass. Let me send you the link for that. So there's the link for Lentech. Let me just make sure that appeared. Okay. And then we have, let's see here, acetaminophen, C8H9NO2. 151.16 grams per mole. So we know that 1 mole of acetaminophen equals 159.16 grams of acetaminophen. Let me make sure I got the right number there. 151.16. So I have the wrong number here. There we go. And then I need to compare moles of acetaminophen to moles of hydrogen. Well, I already told you that in one of these things, there are 9 of those. So in a mole of acetaminophen, there must be 9 moles of hydrogen. And then finally, in a mole of hydrogen, there must be some number of grams of hydrogen, and that's just off the periodic table. So I need to take my 0.2771 grams and just go through the gamut here to solve the problem. So that would be 0.2771 grams times, oh, this is grams of acetaminophen. Grams of acetaminophen turns into moles of acetaminophen. And then moles of acetaminophen turns into moles of hydrogen. And then moles of hydrogen turns into grams of hydrogen. We're just following the blueprint for our units, right? And now we can do the numbers. So in 1 mole of acetaminophen is 151.16 grams. In 1 mole of acetaminophen, there are 9 moles of hydrogen, because we just determined that. And in 1 mole of hydrogen, there are 1.008 grams of hydrogen. And so that's going to equal 0.01663 is what I got. Or if I turn that into milligrams, because I don't know what your problem is actually asking you to do, if it's grams or milligrams. But that's the answer. All right. So the next one, determine percent volume of ethanol if you have 17.6 milliliters of ethanol and 23.1 milliliters of water. Now, as written, this isn't possible to solve because volumes don't add. So I'm assuming that somewhere in the problem statement it says assume the volumes add. Because if it doesn't say that, then it needs to tell you what the total volume is. And if it doesn't say either of those, then the problem can't be solved. Let me scroll this down real quick here. Let's assume that the volumes add then. So then the total volume would be that 40.7. Yeah, that looks right. And so then volume percent is volume ethanol over volume total, which would be 17.6 divided by 40.7. I forgot times 100% here. Since it's a percentage, we need to multiply by a percent. And so when I do that, I get 17.6, 40.7 times 100 is 43.2% VV ethanol. There you go. So that's a volume percentage. All right, examples on how to tell if a reaction is redox or double replacement. So double replacements always swap two things in two compounds, whereas a single replacement swaps two things and only one of them's a compound. So if I had something like this, oops, then I'm swapping these two things. So swap, but only one of them was a compound. So this is single replacement. And as a consequence of this, maybe I shouldn't write an arrow. Single replacement reactions are redox. Now, if I had something like this, I don't need parentheses actually. If I had something like this where I swap these guys, but both of them are compounds, then this is a double replacement. And double replacements are not redox. Now, I can't imagine that I would ask you a question that would be, label this as a single replacement reaction and a redox reaction. I think the only questions about redox I ask you are like, which element is reduced? Which one is oxidized? And then you just look for, oh, which one got more O's on it and which one has fewer O's on it, or something like that. So when you're looking at your equations and you're trying to decide, is this single or double replacement, or is it redox or not? Look for how many of them are compounds, because a single replacement always has an element by itself. Now, that element might be a molecule. So, for example, this would also be a single replacement. So if I had NaCl plus F2, I could make NaF plus Cl2, and then I have to actually go and balance the equation here. So this would be a single replacement because I am swapping these two, and there's still only one compound. Hopefully that answers your question. We already did the pentane combustion. We can do how many grams of neon are in this sample. So let me hit clear again. Remember, you guys, you can pause whenever you want to. So if I clear something too quickly, just pause the video and hit left on your keyboard, and it'll go back a few seconds. Provided you're clicked on the video, not somewhere else. So this is neon. Remember that we can turn atoms into moles by using Avogadro's number, right? 1 mole is Avogadro. So if I know the number of atoms, I know the number of moles. And if I know the number of moles of something, I can figure out the number of grams. And this is from the periodic table. So let me just move this down here. And then we'll turn atoms into moles. And then we'll turn moles into grams. Okay, how many atoms are in a mole? Avogadro's number. And then how many grams of neon are in a mole? Well, that's on the periodic table. I gotta actually get my periodic table. Let's see. And that is 20.18. And then we do the calculation. So 1.58 times 10 to the 24 times 20.18 divided by Avogadro. And I got 52.9 grams of neon. All right, so the next problem, what's the molarity of the solution when 14.7 milliliters of 3.9 molar sodium hydroxide are diluted to a final volume of 200 milliliters? So, oh, oops, hold on. I did this yesterday for a different class, and they use a different formula for it. They use M instead of S. So we can make a little chart for these. So the concentrated stock solution is the higher concentration. We want to find the molarity of the diluted solution. So we're going to find this. Stock solution is 3.94 moles per liter. And I have 14.7 milliliters of it. The final volume of the dilute solution should be 200 milliliters. So I need to solve this equation for CD. So I can divide by VD here. And so that's going to equal the concentrated molarity times the stock volume divided by the dilute volume. You'll notice that the volumes cancel out there, or the volume units. And the molarity I got was 0.290. So that would be the molarity of the solution if I added enough water to the original solution that was 3.94 moles per liter and 14.7 milliliters, it would become 0.290 moles per liter if I increased the amount of solution by adding water to 200 milliliters. All right, I hit the end of your questions, so let me know if you have more. So what I'll do is I'm going to turn the music back on, and I'll mute my mic, and I'll just hang out for like 5 more minutes, and then we'll answer any more questions that you might have. So, see you in a bit. All right. Let's wind this down. Okay, that's enough of that. So let's scroll back to the top. Let me clear everything here. I actually really like that song. I could listen to that forever. I did when I had a Wii. I would just leave it on the shop. But I realized that a lot of people can't stand that that music, which is why I'm like, please ask questions, or else you have to listen to the music. Okay, so we got what volume? What is the volume of a balloon in liters? So, a balloon containing 2.10 grams of nitrogen gas. And so the pressure is 777.2 torr. And the temperature is 21.9 degrees Celsius. Now, this could eventually become a number of moles. So the equation that we're going to be using here is PV equals nRT. Because there is no before-after, right? There's no second temperature, there's no second pressure. Even though they told you PV and T, and you might look at that and think, oh, that's all the variables I have of the combined gas law. It's really not, because you need a before and after, right? So we have to use the ideal gas law here. Now, it's important to note that for R has this value, but it has these units. And so we have to make our units match. So we have grams, which doesn't match moles. So we got to turn grams into moles. We have torr, which doesn't match atmosphere. So we got to turn that into atmosphere. And then we have Celsius, which doesn't match Kelvin. So we got to turn that into Kelvin. So let's do that. So let's start at the top here. So for N, we would need to turn 2.10 grams of nitrogen into moles. So that means doing grams of nitrogen to moles of nitrogen. And in a mole of nitrogen, we could look this up on the periodic table, there are 28.01 grams of nitrogen. So how many moles are there? We'll do the division. 2.10 divided by 28.01. And I get 0.0750. Okay, so now we have N. That one's good. Now we can do P. So this is N. For P, we need to turn this into atmospheres. And I'm guessing this is a question from the textbook, because we need to use this conversion. 760 torr is 1 atmosphere. .023. Oh wait, sorry, only 3 sig figs. 1.02 ATM. There should actually be a dot like that. All right, so that's pressure. And then temperature is 21.9 degrees Celsius plus 273.145. I'm just going to round that to here. And that would equal Kelvin, so connected. Okay, I have an upload again. I got an alert that said OBS is disconnected, reconnecting. So as soon as I saw that, I stopped talking. Hopefully it didn't jump ahead too much. All I did was do the addition of the temperature. So in order to convert Celsius to Kelvin, we got to add 273.1. 21.9 plus 273.1. And I get 295.0. So now I have P, N, and T, and now I just need to solve for V. So if we go down here to solve for the ideal gas law, this is the one I want to solve for, so we'll just rearrange it so that we get V equals nRT over P. And so I'll plug in all the numbers that we just got. So we got 0.0750 moles of N2. R is 0.08206 liter atmospheres per mole Kelvin. And T is 295.0 Kelvin. We'll divide that by the pressure, which was 1.02 atmospheres. And all of that goes in my calculator, and it should give me an answer in whatever unit is left. So moles cancel out, Kelvin cancels out, atmospheres cancel out. Liters is all that's left, so that makes sense. Volumes are in liters. And so punching all that in the calculator, I got 1.78 liters. Is the chat working? Is the chat updating? I'm just going to type a period in there. Hopefully everybody can see that. If it's not working, yeah, okay, it is working. Cool. If it's not working, I'll know pretty quickly when nobody responds to me. All right, so that's how we do that one. So the molarity of the HCl solution, that's the same as the NaOH one that we did before. Dilution works for anything. Even though it's HCl instead of NaOH, you use the same process. So you can refer back to the previous problem that we did for that one. And then how to know vapor pressure, for example, butane. So what I think you're asking in that question is, how do I know the vapor pressure if something is higher or lower than something else? And so the answer to that is so that vapor pressure is affected by intermolecular forces. And vapor pressure itself affects boiling point. Because remember, when vapor pressure equals atmospheric pressure, we get boiling, right? And so some gases have higher vapor pressures, so they boil at a lower temperature because you don't have to heat them up as much to get them to meet this condition that vapor pressure equals atmospheric pressure. Now, if our molecules have strong intermolecular forces, so here are my molecules in the liquid phase. If they have strong intermolecular forces, and that's what these lines are. They're just all held together, so strong intermolecular forces. The result of that is that there are very few molecules in the vapor, and so you have a low vapor pressure. Alternatively, if you have, here's all of my molecules again, and I have very weak intermolecular forces. In this case, my molecules can escape because it's very easy for them to do so. There's nothing holding them in place, right? I'm trying not to spell it the Canadian way, even though I want to. So if there are weak intermolecular forces, then you have a high vapor pressure. So if a question asks you to sort things by vapor pressure, then what it's actually asking you to do is sort them by intermolecular forces. So the way you would do that, to summarize, is that for the scale weak, medium to strong, then the vapor pressure would be high, medium, and then low. So, for instance, water is a very low vapor pressure relative to, say, gasoline, because water can hydrogen bond with itself, and hydrogen bonding is a strong intermolecular force. Gasoline only has dispersion, and so that's a weak intermolecular force. So that's how you'd sort that. I believe that I would only ask you to compare two different substances. So I wouldn't be like, sort butane and hexane and octane in water by their vapor pressure, because that'd be very difficult for you to do. Now, if I gave you all molecules that had the same, like, they were all dispersion forces, then you could do that. Because remember, as molecules get bigger, their dispersion forces get stronger. All right, that's all the questions that are on the chart here. We're actually at break time, so I'm going to put the break timer up on the screen here real quick. And it's more of that music that we love. I just play this for the review session because I find if I put something really annoying, people tend to just like come up with any question. But so I'm going to start the timer. During the break, if you have more questions, please let me know. And if there are no questions by the time that the break is over, then we'll just have our little closing and we'll call it a day. So I'll see you in a little bit after the 10-minute break. Last call for questions. If you have anything, please type it in the chat. Alright, we're back. So I don't have anything in the chat, so I'm going to make last call for questions here. So if you have anything at all you want me to answer, let me know. Just checking to make sure, yeah. Alright, well, it looks like that might be everything. Most people have checked out. So, I'm gonna head over onto here. Yeah, that's all I have. So, what's gonna be coming up next? So there is an exam on Friday. There's a review session next week on Tuesday. I'll post an announcement about that for the final, and then the final exam is next week on the day on the syllabus. Until then, I don't really have anything else to go over. So I do want to thank everybody who came out to the review session. I do want to thank everybody who has posted in the chat, or talked in the Discord, or sent me an email, or whatever for Chem 121. I know that it is very difficult to be an online student. Yeah, you do get 2 attempts on the exam. I know it's difficult to be an online student when it feels like there's a disconnect between you and the instructor. 2 attempts on the final 2, yeah. But by having everybody like so active and engaged and genuinely appearing to care about the class, you make my job a lot easier and a lot more enjoyable. So thanks again for everything. Best of luck on the exam. I'll see you on the review session, and if everything goes well, and this is the last time we speak, well, it's been wonderful and it's been real. Thanks again, and take care.